Hello everyone, I'm Ruichen Ma from the University of Electronic Science and Technology of China. It's a great honor to present our work, I2E, a novel framework for real-time image-to-event conversion for high-performance spiky neural networks. Spiky neural networks are well known for their energy efficiency and the potential for green AI. However, their practical use faces a big drawback: the lack of high-quality and large-scale event data. Existing neuromorphic datasets are not enough for training deep and complex models successfully. Standard data collection methods have big limitations. DVI sensors are costly, have low resolution, and require long capture times. Alternatively, existing conversion algorithms such as ODG provide a software solution but are computationally heavy. Their high latency makes them impractical for integration into real-time training pipelines. This limitation forces researchers to rely on small or synthetic datasets that do not fully capture the complexity of real-world vision. To resolve this bottleneck, we introduce I2E. Our primary objective is extreme efficiency. I2E is a framework optimized to convert static images into high-quality event streams in real time on modern GPUs. This real-time capability is a breakthrough because it enables on-the-fly data augmentation. In standard deep learning, techniques like random cropping and flipping are essential for robust training. Before I2E, applying these augmentations to SNNs was impossible due to the slow conversion process. I2E removes this barrier, allowing us to use standard augmentation pipelines to train deeper and stronger SNNs. The core innovation of I2E lies in its modeling of event generation. The method is inspired by biological vision, specifically the tiny eye movements that human eyes make to see detail. In our framework, we simulate this process mathematically. We do not rely on shifting pixels in memory, which is a slow operation. Instead, we define this movement as a spatial convolution. We contrast a sparse difference kernel to represent the motion. By using convolution on the image intensity map, we compute the temporal change in a single pass. This formulation reduces the computational complexity to O of 1 per pixel. This approach is highly parallel, thus it runs very fast on hardware like GPUs. Beyond speed, keeping signal quality is essential. A common challenge in conversion is selecting the right firing threshold. A fixed global threshold often fails to capture details in low contrast rates or create noise in high contrast areas. To address this, we propose adaptive thresholding. Our method dynamically adjusts the sensitivity based on the local contrast range of each input image. It ensures that, regardless of the lighting conditions, the generated event streams keep sharp contours and rich textures. This high signal-to-noise ratio is vital for training high-performance models. Our experimental results confirm the huge efficiency gains of the method. As shown in the compression, physical device hardware typically requires about 3,000 milliseconds to capture a stable stream. Existing algorithms take around 30 milliseconds, which remains a bottleneck for training. In contrast, I2E completes the conversion in just 0.1 milliseconds. This represents a 30,000-fold speedup compared to hardware capture and a 300-fold improvement over existing algorithms. Moreover, this efficiency translates directly to energy saving. Our method reduced the energy consumption of the first layer by 19 times compared to standard artificial neural networks. This efficiency is a key enabler for scalable, low-power neuromorphic systems. We tested I2E on large-scale ImageNet benchmark. We compared our method against existing event stream datasets based on ImageNet, such as N ImageNet and ES ImageNet. we trained a ResNet SNN on our generated data. We achieved a top-line accuracy of 60.5%, which significantly outperforms all previous baselines, establishing a new state-of-the-art in this domain. This demonstrates that our synthetic data is not only fast to generate, but also rich in useful features required for complex classification tasks. A crucial contribution of this work is the validation of the same-to-real transfer paradigm. A central challenge in the field is determining whether synthetic data can successfully train models for real-world sensors. We address this through a detailed transfer learning experiment. We trained a model on our synthetic I2E data and fitted it on a real-world DVS-CIFAR10 dataset. The outcome was highly successful. We achieved 92.5% accuracy on the DVS-CIFAR10 dataset. This result confirms that our synthetic data serves as a high-fidelity proxy for real-world events. It successfully bridges the domain gap between simulation and reality, enabling researchers to develop robust models without relying on expensive hardware data. In conclusion, I2E resolves a long-standing data bottleneck in SNN research. It provides a fast, scalable, and high-quality solution for the community. We have released all I2E datasets, and our goal is to build a foundational toolkit that accumulates future research. We invite you to scan the QR code to access our open source code and pre-trained models. Thank you for your attention.